Hello everyone, my name is Joseph Lovett, and this presentation is based off the paper An Internal Variable Model of Viscoplasticity by Douglas Bammann. One thing that Dr. Pagan told me about the sponsor of this paper, Sandia National Laboratories, is that they work with and study products that cannot be used twice, is a way of putting it. That is to say that they are interested in materials that are subject to high strain rates and changes in temperature. So, let's take a minute to talk about what can cause the temperature to change within a metal. Baumann's paper introduces the idea that at high strain rates and deformations, it is necessary, not only important, but necessary to consider the effects of temperature, because there is heat being generated by plastic work. So, out of curiosity, why would plastic work generate heat? Well, at the atomic level, as you're plastically deforming them, you are rubbing atoms against each other, causing friction. And when those atoms exceed the resisting force keeping them in place, it snaps back to where it wants to be and vibrates. This increases the temperature of the metal. At least, that's the Google answer that satisfied me. We would expect the stress required to deform a metal to be lower at higher temperatures. And we've even seen these in blacksmithing and glassblowing videos, but instead of heat generated from a deformed part, it was applied externally. So, since this paper focuses on the effects of temperature on the stress strain curve, then we would expect this model to decrease the stress in a stress strain curve due to the temperature generated by plastic deformation. And to spoil the ending of the paper, that is exactly what we see. This is a stress strain curve of where they took the material properties of a stainless steel and modeled it with and without effects of temperature. The top curve corresponds to an isothermal model, so temperature is considered constant and the final temperature is the same as the initial temperature. Since there was no increase in temperature, then there was no decrease in the stress due to softening. The bottom curve does include temperature changes. So as the material point was strained, its temperature increased and softened the material and caused the stress to decrease. This figure makes it clear why Bammann stated that the effects of temperature on the stress strain curve may be necessary to include in the model. There is a significant drop in strength. On the far left, especially during the elastic portion, the stresses and strains are very similar. But as the simulation progresses, the stresses in the model with the increasing temperature drops to about a third of the other. Without considering the effects of temperature on these materials, at these strain rates, a part could be approved for use, but actually be unsafe. Before going into the model, what are the assumptions? Well, first, let's make the assumption that this is an adiabatic process. For this, that just means that the temperature is the same everywhere and all at once. Sure, there may be some temperature gradient inside of real test specimens, since some parts experience more plastic deformation than others, but this is not a thermal paper, so conductive heat transfer is not included. Also, Dr. Bammann suggests that at high strain rates, an adiabatic process is a good assumption. Also, cyclic loading is not a consideration here, so we aren't going to study or model any loading that reverses from tension to compression or vice versa. This should be just fine for Sandia National Laboratories with their one-time use product research. There are some other assumptions that allow us to make a stress-strain relationship, but we won't be using the stress-strain relationship they use in this paper, since we already have a perfectly good model for that. And this is the model. There are two variables that directly impact the hardening and softening of this material. First, we have alpha, which is a tensor, and this allows us to describe the deformation history effects. This corresponds to the internal or back stress acting on a dislocation and the kinematic hardening variables which described the center of the classical yield surface at the microscopic level. This brings us back to the idea of putting our finger in a cup and moving it back and forth. And secondly, we have temperature, which is a scalar that affects the softening term in the material. Unfortunately, temperature is written as a theta, but hey, maybe things were done differently in the 80s. Since these are variables, they need to be tracked in our model's ODE solver with some evolution equation that describes their change over time. Those are the bottom two equations on the right. Together, These allow us to describe the kinematic and isotropic hardening. We've studied this before, so we are familiar with the idea of kinematic hardening up to some saturation level. But in this case, that saturation amount is a function of temperature. Temperature can affect the hardening to the degree, pun not intended, that instead of hardening the material, it can soften it too. So this is a variable kinematic hardening saturation term. Now these other evolution equations that describe tau, delta, and psi, I think it's pronounced psi, are this paper's way of tracking the stress and strain. They become variables that would also need to be tracked, but again, we have a model that already works, so we are going to focus on the hardening and softening effects caused by alpha and temperature. All of these evolution equations are for loading in any direction, and when we consider only uniaxial tension or compression, we can reduce these equations so that we no longer consider rotation as part of the evolution of stress and strain. And these are the two evolution equations for alpha and temperature when only considering uniaxial tension or compression. This works really well for the setup we've already developed in class because first of all, the expressions are shorter and they are also easier to translate into the terminology that we've been using. But also many of the homework assignments we've had so far use isochoric boundary conditions where the material is tensioned in one direction and pulled in half the speed from the other two directions. So we're going to be using the same boundary conditions here. The expression for G is the equation that is inserted into the evolution equation for alpha. Now, let's look at each of these terms and see if we can understand their functionality when being incorporated into the model. The evolution equation for temperature is a function of both the stress and plastic strain rate, and this matches our expectations. We know that temperature increases with the plastic deformation rate, and the faster the plastic deformation, the more frequently the atoms will snap back to generate heat. This would also mean that there is a time at the beginning of the stress-strain curve during the elastic regime that there is no increase in temperature since there is no plastic strain. The temperature growth rate is also dependent on the load, so the higher the friction forces on the atom, the harder they will snap back and the faster they will vibrate to increase the temperature. And this paper proposes that the temperature growth rate is linearly proportional to the stress and plastic strain rate with a material property A. The units for stress and plastic deformation rate work out to be the same as those for power. So A is going to be synonymous with specific heat. It is basically the material's sensitivity to heat generation. The material's temperature would increase faster with a higher A value. This can be found with tension tests where the material's temperature is also measured. This relationship will result in a temperature that is always increasing, because in tension you are going to have a positive stress and a positive plastic strain rate, which results in a positive temperature change. Those are not going to change unless the direction of the load changes, and we have already said earlier that the paper does not cover cyclic loading. Even in compression, both the stress and plastic strain rate will be negative, so using this model, the temperature will always be increasing, because even in compression, you have a positive temperature rate. Now, there could be ways to more accurately represent the temperature increase based on stress and plastic strain rate with maybe a polynomial or an exponential term, but we will see later that this is a very appropriate approximation. So there is no need to make this more complex and gather more constants to similar to A. We will translate this equation into our model by setting stress to be equivalent to von Mises stress, and the plastic strain rate will be the equivalent magnitude of the deviatoric plastic deformation rate, or dP. Here we are going to reintroduce a kind of kinematic hardening through the alpha term. Microscopically, alpha has been associated with the formulation of dislocations into cell walls or subgrains, and the density of dislocations is assumed to increase with the dislocation velocity. The evolution of alpha is assumed to consist of a work hardening term minus a recovery term. Finally, we have gotten to the place where the temperature is included into the model. Now, the last time we saw this alpha term, we were trying to replicate the Bausinger effect, where the material yielded earlier when the load was reversed. We did that by biasing the relationship between the equivalent stress and the plastic deformation rate. When alpha increases, it basically adds more stress to the curve. And then as alpha decreases, it does the opposite by subtracting stress. This format was worth reviewing because the model used in this paper uses it. We can take this format and adapt it to a material that hardens, as materials do, but also softens when temperature becomes a factor. So while the Bausinger effect is mostly noticeable when the load is reversed, this application of hardening and softening will take effect in a single loading cycle. And finally, the bottom equation there is the translated version of the evolution equation for alpha that fits in our model. Here we changed this scalar form into a tensor form to allow for loading in multiple directions. So alpha is a 3x3 tensor, but we will use the same assumptions as before, where it is symmetric and that it is deviatoric. So there will only be 5 more variables to evolve. The nomenclature of K was also changed. That K there is not strength. It is a constant that embodies large strain behavior. To make it different, but still similar, that constant will become KL. The first plastic strain rate term became the tensor version of the plastic deformation rate, and the second plastic strain rate, which is the magnitude term, became the magnitude of the plastic strain rate. This same change was done on the temperature evolution equation. We will set that m exponent to 1, and then we will get to the alpha terms. The SGN function there represents the sign of alpha. This is to maintain directionality when squaring the alpha term. We can get around this by calculating the magnitude of alpha. Since the alpha terms are squared, their directionality is lost. But then it is multiplied by the alpha term again as a tensor. This will both match the functionality proposed by the model and maintain alpha's directionality. It will either be positive times a negative or a positive times a positive. Before moving on, I wanted to cover what each of these terms in alpha's evolution equation will do to the stress-strain curve. We will first have no change to alpha, so there is no hardening or even softening or saturation. It is just a happy little stress-strain curve. This is represented by the blue line on the right. So alpha does not change. If we include the first term in alpha's evolution equation, but we don't include the second term, then we just get hardening. This will increase the stress when compared to the non-hardened stress. The evolution equation for just hardening is represented by the orange line. Then when we finally include some sort of saturation term, the effects of the hardening will decrease and the stress will be lower. This hardening evolution equation does not yet include the effects of temperature and is represented by the green line. The higher the softening constant, the greater its effects, and the lower the stress. Thus we see that with a faster increase in alpha, we get higher stresses, but with a slower increase, the stress does not increase as much. Let's take a minute to see how temperature is affecting the G term. D1 and D2, just like KL from earlier, also embody large strain behavior. Let's first say that D1 is equal to 0 and that D2 is some constant. Well, at the initial temperature, which will be in Kelvin or Rankine, so that we never have a divide by 0 error, that G term is going to be at its lowest because the negative exponent. We have seen earlier that temperature is only going to increase, so the negative exponent will decrease and the value of G is going to approach 1. If D1 is non-zero, then G is going to approach whatever e to the D1 is, but the value of G will always be at its lowest at the start of the deformation and increase with the temperature. This means that the softening effect due to heat generated in the part from the plastic strain rate is greatest at higher temperatures. This, like we saw in the blacksmithing slide, is how we would expect this model to act. A hotter material should become softer, and they are softer. So it is necessary for this model to capture that. All that remains is to pick constants for KL, D1, and D2, and this model can be programmed. And here are the results of the model when using the material properties from homework 5. But the strain rate was increased to the value shown here. And this implementation is very similar to the one presented in the paper, which is about all we can say about the two since they had different constants. One of the properties that we expected to see was that the material's sensitivity to heat would impact the stress-strain curve. The higher the sensitivity, the lower the stress. And that is exactly what we see. The baseline comparison would be a model that does not generate heat, and therefore acts like a kinematic hardening that experiences a saturation level. That case is represented by the blue line. The remaining plots generate heat as they plastically deform and are falling away from the baseline plot as they soften the material. It does appear that there is a kind of saturation level where generating heat no longer has a significant impact on the stress-strain curve. For this implementation, the stress-strain curves did not drop past the stress-strain curve with no hardening. Maybe this is where the model can improve since the metal will eventually melt, but I have a hard time imagining a specimen being tensioned so fast that it melts. When they compared this model to actual stress-strain curves, they found that it was actually really close. When they collected experimental data and plotted the results, they found that the model predicted stresses within about 10% of the plastic regime and about 20% in the elastic regime. And most of the error in the elastic regime occurs around the yield stress when it begins to harden. They found that at strain rates of magnitude 10 to the negative 5, the material acted essentially isotropically. And at high strain rates of magnitude 10 to the negative 2, that the adiabatic conditions were approached within the material. So, when considering a model to use that predicts a material's strength at high strain rates, this internal variable model of viscoplasticity may be a valuable tool due to its simple implementation and accuracy.